Hi, I'm Daniel Chan from UNSW Sydney. Welcome to another adventure in pure mathematics. In this video, I want to talk to you about some very important surfaces in algebraic geometry. They're called Hirzebruch surfaces. So normally when you study these, you need to look at a little bit of surface theory and about things like Castelnuovo's contraction theorem. But if you've set up the technology of toric varieties, these can be studied quite explicitly and in an elementary way. That's what I want to do in this video. So before we begin, I want to make a small scholium, which is going to help us do the analysis of the combinatorics involved when we study these toric varieties. And it's the following. So remember when we construct these toric varieties, monoids M inside some lattice like this, Z to the N, and we look at the monoid algebra. And so these are the affine varieties that we glue together to form our toric variety. Okay? And the key point, which is a very simple observation, is that if you look at this monoid and the corresponding monoid algebra, of course, the isomorphism class of this algebra, okay, depends only on the isomorphism class of the monoid M. Okay, so we're going to use this quite a bit. And in particular, some of the calculations that you do, if, for example, you just do a change of basis of this Z to the N, you're going to get something isomorphic, okay? So you'll get the same type of variety. Okay, so let's start with the simplest of the Hirzebruch surfaces. This is probably something that you all one, just P1 cross P1, which is the zeroth Hirzebruch surface. So we denote it with this F lower 0. So how do we get at P1 cross P1? Remember, if you want a toric variety, we need a fan. And the fan we'll look at will be inside two-dimensional space, okay? And it's basically given by these 4 cones and their faces. So the 4 cones are given by the 4 possible quadrants. So let's just see roughly why on earth this fan does indeed give us a P1 cross P1. It's not a difficult calculation, and if you know the fan that gives you P1 and understand how that's a toric variety, it should be fairly easy. So basically the fan that gives you P1, okay, just to remind you, is basically now you're in dimension 1, so you just look at one of these axes, and the 2 cones are basically the positive axis, and the other one is the negative axis, and of course you have the intersection, which is the 0. So that gave you the P1. So more generally, how do you work out that this is P1 cross P1? Okay, so firstly what you do is that you look at the dual cones. Okay, so here I've got one cone, I've labeled it sigma plus plus because the x and the y axes, the coordinates rather, they have to be non-negative, so I'll label it sigma plus plus. And what you do is you look at the dual cone, so what are all the points which have positive or non-negative dot product with every vector inside here. Of course, it's the same cone. Okay, so the sigma plus plus check is the same as sigma plus plus. The dual cone is the same. And that means that this cone here will give us one of the affine toric varieties, which will give us an affine patch of this, the toric variety associated to this fan. So what's that? So basically you just look at the monoid algebra of this. The monoid algebra of this is essentially just the polynomial ring in x and y. So you're just looking at non-negative powers of x and y. So you just have the polynomial ring in x and y. Okay, that's the monoid algebra that you get here. And of course, that's just the coordinate ring for the affine plane, coordinates x and y. Of course, these other 3 cones, okay, they give you monoids as well. So remember, the monoid that you're looking at is just the integer lattice points inside these cones, right? So basically, z to the 2 intersected with what you see here. So here, what you'll find is that the powers of x you get are negative, and the powers of y are still non-negative, okay? So here, well, since this is isomorphic to this one here, okay, you also get an affine plane. But in this case here, what you'll get is it's the affine plane whose coordinates are naturally x inverse and y. You can also work out the dual cone to this one here, which will be the upper half plane, okay? And then you can glue together these two affine planes to get something. And it's not difficult to see what you get here, okay? You've got a y variable, okay, which can be anything. So that gives you a copy of A1. And then since you have both x and x inverse, basically you get a P1 cross that, okay? So that's why you get this kind of P1 behavior. Similarly, if you work with the other two cones, what you get here is you'll get a copy of the affine plane, but with coordinates x inverse and y inverse. And finally here, a copy of the affine plane with coordinates x and y inverse. And glue them together in kind of the obvious way. And I hope you can see that it will take a little bit of work to actually do the calculation, but you'd expect to get something like P1 cross P1, and that's indeed what you get. So this is rather nice that if you want to split P1 cross P1, this is indeed firstly a toric variety. Okay. It's very easy to see why it has a dense torus in here. For example, inside P1, there is a copy of C cross, okay? And similarly here, so there's a copy of C cross to the squared, okay? And so this is a toric variety, and it's just given by this data here, okay? So the first thing that you can do. So if you want to modify this, one of the things that you can do is form a blowup, okay? So we saw an example of how this blowup works. So what you can do, if you want to blow up the affine plane, such as this one here, let's say this affine plane, the way to do that, torically, is you break up this cone into two cones. So this is the affine plane. So it's generated by, basically, if you look at the monoid, it's generated by this lattice point and this lattice point here. Okay, this lattice point -1, 0, and this lattice point 0, -1. And what you can do is you can break this up into two by basically looking at the ray that goes through the sum of these two. So that'll be 1, 1. So this is the point, or rather -1, -1. So there's -1, -1. So you break that up, and that gives you a blow up of that point there. And hence, on that patch, you can blow up a point that gives you a new surface, and everywhere else, okay, you leave it as is. Since this is a fan, okay, it satisfies the axioms to be a fan. If you look at how the cones intersect, it's all fine. So this is a fan. So this is also a toric variety, and it's also a surface, and it's basically the surface that you get when you blow up the point corresponding to breaking this cone up into two pieces. Okay, and so that's what you have there. Okay, so that's all very well and great. That shows you one of the things that you can do, but perhaps something that's not that new. Okay. So what's the next thing that you can do? What we're going to do now is we're going to look at the reverse of this process. Okay. So what we're going to do is now we're going to, instead of breaking up one of these cones into two, we're going to join up these two cones into one. That's what we're going to do. We're going to join them up. And so what's the point here? I claim there's a map from here to, let's just do that. And this is a new toric variety because it's a fan, it's a legitimate fan, okay? And I claim that actually what you get here is just a blow-up map. But it's a blow-up map corresponding to breaking up this cone into two pieces. Remember, if you break it up, so why can you do that? Okay. So the first thing to notice here about what you have is that you look at the various cones. This is, again, just a copy of the affine plane. This is a copy of the affine plane. And if you remember how it worked when we do the blow-up of a cone like this will also be a copy of the affine plane. But what is this here? If you look at this monoid, you can see that actually it's just the free commutative monoid generated by this lattice point and this lattice point. Okay. Every lattice point inside here you can write uniquely as, well, you go down here a certain amount, so some non-negative integer multiple of that, and then you add a certain amount of this vector here, okay, this 0, 1 vector, so you go up a certain amount, okay? So that means it's freely generated by these two, and so by the Scoldian, really, it's isomorphic to the monoid that you get from this quadrant here. So in other words, this is actually the cone here gives you an affine toric variety, which is just another copy of A2, okay, the affine plane. So really, this surface here is a union of four affine varieties, and they're both they're all just copies of the affine plane, as it turns out. Okay, so this is still smooth, okay, which is rather nice. If we want to blow this up, okay, I guess we can blow up at various places by breaking up any of these 4 cones. Let's break up this one for a change, okay? If we break up this one, how do we break it up? We have to break it up by adding a new ray, which goes through the sum of these 2. So here, this is like -1, -1, and then you have to add this, so you go up to here. So you basically add in this ray. You broke up this here, adding this ray here. So that's a blow-up map, and in particularly, this is a morphism of algebraic varieties, okay? And basically, it just contracts that the exceptional curve, okay? So that's what happens when you have a blow-up, okay? So that's rather nice. We managed to blow this up here, and we know that you can actually blow down. In other words, there is a smooth surface here, such that its blow-up is isomorphic to this one here. Okay. And that's rather nice that you have this configuration. So here from this F0, this 0th Hirzebruch surface, you can blow up, blow down, and you get the first Hirzebruch surface, which is F1. Well, you may have thought, well, you know, it's fairly symmetric, this and this here. Maybe I could have, you know, blown down by removing that. Fine. By the same argument, I could have done this one instead, and I can still join up those 2 cones in this stage here. What happens when I join up those 2 cones, okay, by a symmetric argument? Let's see what we get, and it's shown over here. Once we remove this, okay, now you're only left with 3 cones, these 3 here. And if you remember from some of my videos earlier in this playlist, you'll remember that this is the fan corresponding to the toric variety P2. Okay, so hopefully this is a fact that you already know, but if not, this is a very, very interesting fact about algebraic geometry. Okay, I guess there are kind of 2 most elementary ways to generalize the affine plane to the sort of projective setting. There's P1 cross P1, so that's, and there's also P2. And they're related in this very simple way. You just blow up once, this P1 cross P1, and blow down twice to get to P2. Okay, so that's rather interesting. This is a bit of a special case, but let's see where else we can go from here. What other types of things that we can do in terms of blowing up and blowing down. Okay, so what we're going to do now is we're going to do some more blowing up. We're going to take this cone now, okay? And we're going to blow up a point corresponding to this cone. Okay, so let's just see. So remember, this is a copy of the affine, gives you a copy of the affine plane. And the generators for the monoid, the free generators are this lattice point, -1, -1, and this lattice point, 0, -1. So if we want to blow up, we need to add in an extra ray in here, okay, an extra face, by breaking this up into 2 cones, okay? And then this will go through this lattice point here. So you add this to this, so you get this one here, which is -1, -2. Okay, so you do that. And when you do that, you break up that cone, and you get an extra cone like that. So this goes through the lattice point, -1, -2. Okay. This is a blow up. And again, this is now what was an affine plane is a union of 2 affine planes. So this blow up is a union of 5 affine planes. In particular, it's going to be smooth, which is rather nice. And then what are we going to do about that? Okay, so that's great. You get a new surface. It's just a blow up of this. And it's quite explicit because not only do we know it's the union of 5 affine planes, but you also know and can work out explicitly how to glue them together, because this combinatorial data of this fan gives you all that gluing data. Okay, that's kind of what's going on when we draw that picture. Okay, so we actually can continue this blow up, blow down procedure, because I claim that you can actually blow down. How do I do that? So I want to join 2 cones, and I claim now that I can join this one and this one. Okay. So I join these 2 ones and this one. So why can I do that? So basically, I want to show that, let's just join them together. So I'm going to remove that, just draw what I have. So you just get this cone here. This will go through the point -1, -2. Okay, that's here. And remember, this cone here is also corresponds to a copy of the affine plane, because the monoid here is freely generated as a commutative monoid by two elements. It's by this lattice point and 0, 1. Okay, so to get any lattice points here, you can slide down as many integer times multiples of this as you like, and then you just go up rank 1. And that's telling you that, yes, this will give you the free commutative monoid on generated by two elements. And so basically, when you look at the monoid algebra, you'll just get the polynomial ring, but it's a polynomial ring, and the generators will be, well, this one here will be y, but this one here, I guess, is x inverse y to the minus 2, right? So they're the polynomial generators for the corresponding monoid algebra, and so you get a copy of A2. And if you want to work out, well, how do you blow this up? So I guess you have to add those two things together. So you add this vector here to this one here, and of course, that's the one that you have here, okay? This one here, rather, okay? So that's the extra one that you have there. So indeed, you can actually blow this down now, and we can do it torically, so we know it very, very explicitly, and then you see that that's what's happening. Okay, so just roughly to see what happens, if you want to see what happens when you go from F0 to F1 to F2, essentially, in all cases, F0 here, F1 here, and F2 here, you see there are always 4 cones. That means that the surface is a union of 4 affine planes, okay? But how does it change, okay? So here, these right two are always the same. But if on the left, this here moves down. This goes down to there, and then it moves down to here. And you'd expect that if you can do it this many times, that the procedure could continue, and you can keep sliding this down, okay? And basically each time, this ray will go through the lattice point, which is one below. That's what's going to happen. Okay, that's what's happening each time, one below. And if you look at that, that's for the nth surface, and you get it by this procedure of blowing up and blowing down. And that's how you can study these Hirzebruch surfaces from the point of view of toric geometry. I hope you enjoyed this lecture in pure mathematics.